In this video, I wanted to do a bit of a deep dive into Unity's CullingGroup API and explore some use cases to help optimize your code. Hi, I'm BGK of Pear Tree Games, and this is how to optimize your Unity game with CullingGroups. First, let's discuss what a CullingGroup is. Basically, a culling group is a group of spheres which hook into Unity's culling and LOD pipeline to take advantage of visibility or distance calculations and events. griptutorial.com has a great breakdown with a couple simple examples which showcase this behavior. Link in the description. So, if you have a large number of things and you need to test for visibility or distance, it's an extremely simple and optimized solution. The API documentation even has a list of possible scenarios where this could be useful. The scene we'll be working on is a modified version of the core third-person controller project. I've added a spawner game object, which will spawn enemies at spawn points which are within a certain ringed distance of our player, which we can see there as the red wire spheres. We'll also despawn them if they're beyond the distance of the largest sphere. Each spawn point can only have one enemy at a time, and we'll have about 150,000 spawn points generated using Sebastian Legg's Poisson sampling, link in the description. The points will be yellow if empty, or red if occupied by an enemy. In a real game, you'd probably partition out the scene into smaller scenes and load them in as needed, but this is better for testing purposes and easier to set up. Once our enemies have spawned, they will patrol a small area and chase the player if they get too close, which is shown by making them a nice vibrant magenta. While they're patrolling, we'll also make them calculate the square root of 1 to 10,000 just to get them to work a bit more for this test since our scene is relatively simple. Before we optimize our code, let's look at our profile to see what methods are taking the most time. As you can see, the enemy_spawner.update method and enemy.update method are taking the bulk of our entire CPU frame time. Let's jump into the code to see how it currently works, and then we can work on our optimizations. Our enemy spawner has a reference to our player, a spawn distance, and a spawn ring width. It then has an array of points and enemies. When we awake, we set all of our points using Sebastian Legg's Poisson sampling and the enemy array to the same length. We also just like to say how many we've done. Then, in our update loop, for each point that we have, we will get the distance to the player from that point, check to see if there's an enemy at that spawn point already, if we are within the spawn distance, or if we're outside the spawn distance. If we're within the spawn distance and there is no enemy at the spawn point, we will spawn an enemy, which for this is just a sphere, setting the transform, adding a nav mesh and setting the speed, and finally adding an enemy component and returning. If we're outside of the spawn distance and there is an enemy at the spawn point, we will destroy the enemy game object and set that value to null in our array. Our enemy model behavior is a very, very simple state machine. I would not recommend this for any actual gameplay, but this is a very quick test, so it's okay. Again, we have a reference to our player transform, a chase distance, and when we should go back to patrol distance, a starting position, a state, our nav mesh agent, and a mesh renderer to change the color. We then set up our components and set a patrol destination on enable, which will simply grab a unit, which will simply grab a point near our starting position and set that as our nav mesh agent destination. In our update loop, we will get the distance to the player, and then if we're in the patrol state, our color will be gray. If or our distance to the player is less than our chase distance, we will start to chase them. If we are at our current destination, we will set a new patrol destination. And lastly, we'll just do some extra calculations just to increase their amount of effort. And if we are in a chase state, we'll set the color to magenta. Check if we're far enough from the player, then we will change our state back to patrol. Otherwise, we will set the destination to our player and we'll just slightly increase it so that we're above the nav mesh. If you're under it, then it will be an invalid value. And that's it. So how can we optimize this? For our spawner, we'll create a local culling group and turn all of our spawn points into bounding spheres. Then we'll set up distant bands from our player to see if we should spawn or despawn an enemy, which will be triggered in a callback. We'll populate the bounding spheres array with all of our point locations and a radius of 1, which is about twice as much as our spheres that we're generating, or enemies. Next, we'll set the bounding spheres in our culling group and the distances for our bands. And we'll want to set the reference point to our player and the target camera to our main camera. Now, our callback, which will be called whenever any of the spheres change their visibility or distance. If we're greater than our distance, we will destroy. But if we're in our ring bound, then we'll want to create our enemy. Of course, we'll want to set and update our player reference distance on every frame. But we're still not destroying the enemies. Something's wrong there. We'll also check if the spawn point is visible or not, so we don't pop out our enemies while we're looking at them. So now only spawn points which are out of camera's view will spawn an enemy. Another optimization that we can make is on our enemy. We can use the mesh renderer and check if it's visible, and then only if it's visible will we do these extra calculations. I'd also like to mention you could also accomplish a lot of these calculations manually with the jobs and burst system with a bit more setup and thought, but it is possible to achieve similar or even better results depending on what you're trying to do. And in terms of simplicity, it's really hard to beat the CullingGroups. The API documentation also has a great little section on best practices, which I recommend going through. But one important point is the bounding spheres array is not copied by the CullingGroup, so changes can be made to the array without reassigning the entire thing, and multiple CullingGroups can reference the same array. I hope this helps you in thinking about optimizing your own game. Even if not this exact scenario, there are still plenty of times where visibility and distance checks can be used. Just be sure not to preemptively optimize too much. Look at the profiler, see where you can optimize, then dive in and see what you can do. Thanks for watching.